Why the first humans on Mars will never come back. Tonight, we're about to examine one of the deepest questions humanity has ever faced. Not simply whether humans can arrive on Mars, but whether the first individuals who walk across that vast red landscape will ever make the journey back to Earth. You've likely heard endless discussions about missions to Mars, about settling the red planet, about humanity expanding into the cosmos. But there's something most people rarely stop to consider. The first humans who finally reach Mars may not be embarking on a temporary expedition. They may be accepting a journey with no return. And before tonight is over, you'll understand why bringing them home could be beyond our capabilities, why people would still volunteer to go, and what such a decision could mean for the future of human civilization. Before we continue, if exploring the mysteries of the universe fascinates you as much as it fascinates us, take a moment to like the video or subscribe to the channel. It may seem like a small gesture, but it helps these ideas reach more curious people like you. Now, let's move forward. Think about every major exploration effort throughout human history. Every voyage into territories nobody had mapped, every crossing over unknown seas, every attempt to stand atop a mountain no human had conquered before. What was the one thing they all shared? The explorers eventually returned home. Magellan's surviving crew completed their voyage around the globe and sailed back to Spain in 1522. Edmund Hillary reached the summit of Everest and later made his way safely down to base camp. The Apollo astronauts traveled all the way to the moon and returned to Earth, splashing into the Pacific Ocean only a week later. Every exploration mission, regardless of how dangerous it was or how distant the destination seemed, always included a path back home. Returning was never optional. It was built into the mission from the very beginning. Human exploration has always followed the same pattern. People ventured outward, uncovered something unknown, and eventually returned home to share what they had seen. Mars could completely change that pattern. Mars is not comparable to the moon. The moon is incredibly nearby on a cosmic scale. It sits around 384,400 kilometers from Earth, or about 238,900 miles away. The Apollo crews reached it in roughly 3 days. From launch to splashdown, those missions usually lasted somewhere between 8 and 12 days depending on the flight. While standing on the lunar surface, astronauts could actually look back and see Earth suspended in the darkness, glowing like a blue and white sphere against the blackness of space. They were always only a few days away from returning home. If a serious problem occurred, if an emergency developed, rescue or assistance was at least theoretically possible. The communication delay between Earth and the moon was only around 1.5 seconds. Mission Control could speak with astronauts almost instantly, helping them solve issues, make choices, and coordinate actions in near real time. Mars is completely different. On average, Mars sits about 225 million kilometers away from Earth. That equals roughly 140 million miles. And even that number is misleading because it's only an average distance. Earth and Mars are both constantly orbiting the Sunday. Sometimes the two planets are relatively close together on the same side of the solar system, and other times they end up separated on opposite sides. During the closest alignment, known as opposition, Mars can come within about 55 million kilometers of Earth, or approximately 34 million miles. But at the greatest separation, when the Sun lies between the two planets, the distance expands to nearly 400 million kilometers, around 248 million miles. The gap is always changing because both worlds are continuously moving along their orbital paths. This leads directly to the first major challenge of any Mars expedition: timing. You cannot simply launch toward Mars whenever you choose and expect everything to work out. Missions have to wait for a specific launch window, a period when Earth and Mars line up in the proper positions relative to one another. Those opportunities only appear about every 26 months. If you miss that window, the next opportunity will not arrive for more than 2 years. And once the journey begins, there is no quick trip. Reaching Mars requires somewhere between 6 and 9 months of travel depending on the chosen trajectory. 6 to 9 months drifting through the emptiness of space inside a confined spacecraft, relying entirely on recycled air, preserved food supplies, and systems that cannot fail. There is no easy way to turn around midway through the voyage. The crew will slowly watch Earth fade farther and farther into the distance until it eventually looks no different from any other bright point in the sky. As they travel farther away, communication delays with Earth become increasingly severe. At the closest distance to Mars, radio transmissions still require around 3 minutes to travel one way. If an astronaut sends a message to mission control, Earth will not receive it for 3 minutes. Then the reply from Earth needs another 3 minutes to travel back. Even under the best conditions, a simple exchange takes at least 6 minutes. When Mars is farther away, the delay becomes dramatically worse, exceeding 20 minutes in each direction. A single conversation can require more than 40 minutes just to exchange a few responses. That completely eliminates real-time communication. Astronauts cannot simply ask a question and immediately hear guidance from Earth. They send information, wait in silence, receive an answer later, then wait again. Communication becomes more like exchanging letters across vast distances than speaking over a phone. And if a serious emergency develops during those 6 to 9 months in transit, the crew must largely face it alone. Mission Control may still provide recommendations, but by the time those instructions arrive, the situation could already be resolved, for better or worse. But imagine they succeed. Imagine the spacecraft survives the voyage without catastrophic damage. Imagine the astronauts stay healthy, the life support equipment continues functioning, and the navigation systems remain accurate. After 6 to 9 months crossing interplanetary space, they finally approach Mars. Engines ignite to slow the spacecraft down. The crew enters orbit around the planet. Then they prepare for what may be the most dangerous stage of the entire mission, landing. Landing on Mars is unbelievably difficult. The Martian atmosphere is thick enough to generate extreme heat during descent, which means spacecraft require heat shields. Yet the atmosphere is also far too thin for parachutes alone to slow the vehicle effectively. Mars's atmosphere is only around 1% as dense as Earth's atmosphere. A parachute capable of safely lowering a capsule to Earth's surface accomplishes very little on Mars. Additional systems become necessary. Retro rockets must fire correctly. Timing must be exact. Every component has to function perfectly. If the parachute opens too early or too late, disaster follows. If the retro rockets activate at the wrong altitude, the landing fails. If even a small malfunction appears during descent, the spacecraft crashes into the Martian surface. There is no backup attempt, no second opportunity. You get one chance. NASA refers to this terrifying phase as the 7 minutes of terror. That is approximately how long it takes for a spacecraft to plunge through the Martian atmosphere and descend to the ground. During those 7 minutes, automated systems must independently make thousands of decisions because the communication delay prevents mission control from intervening. By the time engineers on Earth receive confirmation that the spacecraft has entered the atmosphere, the landing has already happened several minutes earlier. The spacecraft is either safely on the surface or completely destroyed before Earth even knows the outcome. The crew monitors their instruments carefully, follows every procedure exactly as trained, and hopes each system performs as expected. During those 7 terrifying minutes, they are essentially passengers, placing complete trust in machines engineered and tested on Earth to operate flawlessly on Mars. And imagine that everything succeeds. The landing sequence functions perfectly. The retro rockets ignite at precisely the correct time. The spacecraft settles safely onto the Martian ground. Human beings are now standing on another world. They have become the first people in history to walk across the surface of Mars, witnessing something no human eyes have ever witnessed before. Around them stretches a rocky wasteland beneath a rust-red sky, mountains visible in the distance, while the fading sunlight casts long shadows across the desert horizon. It is the kind of achievement humanity will remember for as long as civilization survives. But there is one enormous problem. They cannot easily leave. Here's the reason. Escaping Mars is nearly as difficult as reaching it in the first place. To depart from the Martian surface, you need a rocket powerful enough to launch upward, reach escape velocity, and begin the long return journey toward Earth. That rocket requires fuel, an enormous amount of fuel, far more than astronauts could realistically transport during the original mission from Earth. The spacecraft that carried them to Mars was engineered mainly for landing, not for launching back into space afterward. Most of its fuel was already consumed during descent, burned away while slowing the spacecraft, stabilizing its fall, and ensuring a controlled touchdown. The remaining propellant is nowhere near enough to overcome Mars's gravity and send the crew home again. That means an entirely different rocket would have to be waiting there already. A dedicated Mars ascent vehicle would need to be delivered in advance, fully prepared and fully fueled, before the astronauts even arrive. But then another problem appears. How do you transport that rocket to Mars in the first place? You would have to launch it years earlier, land it safely on another planet, and somehow guarantee it still works when the crew finally reaches Mars months or even years afterward. That vehicle would sit exposed to the brutal Martian environment the entire time. Temperatures there can fluctuate from minus 125 degrees Celsius to plus 20 degrees Celsius. Dust storms can engulf the surface for weeks or months. Radiation constantly bombards exposed equipment. Every mechanical system slowly deteriorates under harsh conditions. Yet despite all of that, the ascent vehicle must function perfectly at the exact moment the astronauts desperately need it. And even that challenge is not the most difficult one. The greatest obstacle is fuel itself. Rockets are overwhelmingly made of fuel by mass. The Saturn V rocket that carried astronauts to the moon had a fully fueled mass of roughly 2,800 metric tons. That equals about 6.1 million pounds. Out of that total weight, around 2,600 metric tons consisted purely of propellant. Only about 43 metric tons represented the actual command and service module that traveled to the moon and returned. In other words, the rocket was approximately 93% fuel by weight, and that mission only traveled to the moon, a world with 1/6 of Earth's gravity and no atmosphere at all. Mars is different. Its gravity is about 38% of Earth's gravity. That is weaker than Earth's pull, but still much stronger than the Moon's. Mars also possesses a thin atmosphere, and during ascent, that atmosphere creates drag against a departing spacecraft. Leaving Mars therefore demands a large rocket, and a large rocket requires enormous quantities of fuel. If humanity wanted to launch a crew of 4 or 5 astronauts, along with equipment from the Martian surface, and send them safely back to Earth, the vehicle would likely need to be comparable in size to the massive rocket SpaceX is currently developing for Earth launches. And almost the entire structure would still be fuel. Transporting that amount of fuel from Earth is not practical. The mass becomes overwhelming. If engineers attempted to land a fully fueled ascent vehicle directly on Mars, the spacecraft carrying it would become so heavy that it would require even more fuel simply to land safely. That additional fuel would increase the mass further, demanding even more fuel again. The cycle keeps growing worse. More fuel increases weight, which demands more fuel for landing, which increases weight even more, continuing endlessly until the calculations stop making sense. So scientists proposed another solution. Instead of transporting fuel from Earth, manufacture it directly on Mars. The idea is to use Martian resources, especially carbon dioxide from the atmosphere and water ice buried in the soil, to create methane and oxygen propellant. This concept is known as in situ resource utilization. The process would involve sending specialized machinery to Mars capable of extracting carbon dioxide from the atmosphere, mining underground ice deposits, separating water into hydrogen and oxygen through electrolysis, then combining the hydrogen with carbon dioxide using the Sabatier reaction to generate methane and water. The methane and oxygen could then be stored as rocket fuel. Chemically, this is entirely possible. Scientists know these reactions work because they have already been performed successfully in laboratories on Earth. In theory, the chemistry itself is relatively straightforward. The Martian atmosphere consists of about 95.3% carbon dioxide. That gas can be collected, compressed, purified, and fed into chemical reactors. Water ice is also present within Martian soil, especially at high latitudes and inside permanently shadowed craters near the poles. It can potentially be extracted either by heating the soil or drilling directly into buried ice deposits, allowing sublimated water vapor to be captured. Once water becomes available, electrolysis can split it apart into hydrogen and oxygen. Two molecules of water separate into two molecules of hydrogen and one molecule of oxygen. The hydrogen is then mixed with carbon dioxide through the Sabatier reaction, first identified by French chemist Paul Sabatier in 1897. A single molecule of carbon dioxide combined with four molecules of hydrogen produces one molecule of methane along with two molecules of water. The process is exothermic, which means it gives off heat, helping sustain the reaction itself. The water created during the reaction can be cycled back through electrolysis to produce additional hydrogen, forming a mostly closed system where the primary ongoing input is carbon dioxide collected from the Martian atmosphere. The resulting methane and oxygen are then converted into liquid form for storage purposes. Liquid methane remains stable at -161 degrees Celsius, while liquid oxygen remains liquid at -183 degrees Celsius. Both temperatures are colder than even the harshest naturally occurring conditions on Mars, meaning active refrigeration systems powered by electricity are absolutely necessary. Storage tanks must also be carefully insulated to reduce boil-off, the slow evaporation of cryogenic fuels over long periods of time. No insulation system is perfect, however, so some amount of propellant will always be lost. If fuel production begins months or even years before astronauts arrive, a considerable portion of the stored propellant could disappear through evaporation before anyone ever uses it. And carrying out this process on Mars is far more difficult than performing it inside a stable laboratory on Earth. You need energy, enormous amounts of energy, to operate the atmospheric extraction units, electrolysis systems, chemical reactors, and liquefaction equipment that turns gases into storable cryogenic liquids. A propellant manufacturing facility designed to produce 30 to 50 metric tons of fuel over roughly 18 to 24 months could demand between 100 and 200 kilowatts of uninterrupted electrical power. That is approximately equal to the electricity used by around 70 to 140 average American households. But Mars has no electrical infrastructure waiting for you. One possible solution is solar power. Mars receives much less sunlight than Earth because it orbits farther away from the Sunday. At Earth's orbit, sunlight delivers around 1,368 watts per square meter. At the average orbital distance of Mars, that number falls to roughly 590 watts per square meter, less than half the energy available on Earth. And even that measurement only applies at midday under clear skies near the equator. Once you include nighttime, seasonal shifts, airborne dust, dust coating the panels, and changes in the sun's angle, the average energy output becomes dramatically lower. To meet the required energy demands, you could need several thousand square meters of solar panels, all of which would have to be deployed, wired together, monitored, maintained, and constantly cleaned. Dust presents one of the greatest challenges on Mars. During dust storm seasons, which may continue for months at a time, the atmosphere can become so thick with suspended particles that sunlight levels drop by 50 to 99%. Planet-wide dust storms appear roughly every 3 to 4 Martian years. When these events occur, solar energy production collapses. The Mars exploration rover Opportunity was lost during a massive dust storm in 2018 because its solar panels could no longer generate enough electricity to recharge its batteries or operate its heating systems. The rover froze permanently and never recovered. A fuel generation facility depending completely on solar energy could suffer exactly the same outcome. Nuclear energy offers a far more dependable alternative. NASA is currently developing a kilopower reactor capable of producing 10 kilowatts of continuous electricity using a uranium fission reactor, roughly the size of a trash can. A fuel production operation would likely require 10 to 20 of these units. Another possibility would involve a larger reactor capable of generating 100 kilowatts or more through a single installation. The Soviet Union successfully operated nuclear reactors at isolated Arctic facilities for many years, proving the concept is technically possible. However, transporting nuclear material to Mars introduces both political controversy and safety concerns. What happens if a launch vehicle explodes during ascent? What if radioactive debris spreads across the launch area or falls back onto Earth? These dangers can be managed, but they are not insignificant. Once the reactor reaches Mars, cooling becomes another major engineering challenge. Water cooling systems like those used on Earth are impractical because accessible liquid water is extremely limited and mostly frozen beneath the surface. Instead, the system would rely on radiative cooling, using large thermal radiators that release excess heat into the thin Martian atmosphere to monitor temperature, pressure, chemical composition, flow rates, electrical output, and structural stability. Automated control systems would need to make thousands of adjustments every day, regulating valves, activating or shutting down pumps, controlling reactor performance, and managing battery systems. Maintenance robots would also be necessary to replace damaged components, remove dust from solar arrays, and repair broken electrical connections. All of these systems must survive in an environment filled with dust, extreme cold, and intense radiation, where repairs are difficult and replacement parts cannot simply be delivered when something breaks. Temperatures on Mars fluctuate dramatically. Near the equator, daytime temperatures during summer can climb to 20 degrees Celsius, but once night arrives, temperatures can plunge down to minus 73 degrees Celsius. In regions closer to the poles, or during the Martian winter, temperatures can plunge to minus 125 degrees Celsius. Under conditions that extreme, many materials begin to fail. Seals become fragile and split apart, lubricants solidify, batteries rapidly lose efficiency, and electronic systems start reacting in unstable and unpredictable ways. Every single piece of equipment has to be engineered to endure thermal swings spanning more than 200 degrees Celsius, repeatedly, every day, across many years of operation. Radiation never stops. Cosmic rays and intense solar radiation constantly strike the Martian surface. As time passes, that radiation slowly destroys electronics, causing memory corruption in computers, lowering the efficiency of solar panels, and making plastics and composite materials increasingly brittle. A fuel production facility operating autonomously for 2 years before astronauts even arrive would already accumulate substantial radiation damage. Protective shielding can reduce the danger, but shielding increases mass. Every extra kilogram dedicated to radiation protection is one less kilogram available for fuel processing systems, scientific payloads, habitat equipment, or survival supplies. Mission designers are forced into continuous compromises between safety and performance. And the amount of fuel required is enormous, actual tons of it. A Mars ascent vehicle could require anywhere between 30 and 50 metric tons of propellant just to reach orbit around Mars and begin the trip back toward Earth. 50 metric tons equals 50,000 kilograms, or around 110,000 pounds. To visualize that scale, it is approximately equal to the mass of 35 automobiles. Every bit of that fuel must be produced directly on Mars, using local resources, with machinery transported from Earth, and expected to function autonomously for months or even years inside one of the most unforgiving environments anywhere in the solar system. The speed of production depends entirely on how large and efficient the system is. A highly optimized setup might generate between 100 and 200 kilograms of propellant each day. At that pace, creating 50 metric tons of fuel would still require roughly 9 to 18 months of non-stop operation. And if anything goes wrong, if a pump breaks, if a reactor shuts down unexpectedly, if a dust storm blocks sunlight from reaching the solar arrays, the entire production process halts. The schedule begins slipping further behind. The launch window for the crew's return starts getting closer. Engineers back on Earth watch anxiously as days become weeks and weeks become months, hoping the systems recover, hoping enough propellant can still be manufactured before time runs out. If fuel generation proceeds too slowly, The astronauts are forced to remain on Mars longer than planned. That means consuming additional life support resources, enduring longer radiation exposure, and increasing the likelihood of critical equipment failures. Life support hardware gradually deteriorates. Air recycling systems gather contaminants over time. Water purification systems clog with mineral buildup. Spacesuits eventually develop tiny leaks. Everything experiences wear. Redundancy can reduce the danger, but there are limits to how many spare components can realistically be transported from Earth. If a crew arrives expecting an 18-month mission, but ultimately remains for 30 months, because fuel production falls behind schedule, they are surviving far beyond the operational margins the mission was originally designed for. Eventually, something breaks. Maybe the failure is manageable. Maybe it isn't. Perhaps the astronauts manage to improvise repairs. Perhaps they cannot. If production completely stops for any reason, if the reactor permanently fails, if solar panels remain buried beneath dust for too long, if any essential component becomes unusable, then the astronauts lose all ability to leave Mars. They become stranded indefinitely, forced to wait for another cargo mission from Earth carrying replacement parts, assuming Earth even has replacements prepared, assuming the next cargo launch occurs on time and lands safely. Assistance might not arrive for years. During that time, the crew would have to survive using steadily shrinking supplies, carefully rationing food and water, stretching every available resource to its absolute limit, while hoping they remain alive long enough for resupply to arrive. This is the heart of the problem. Reaching Mars is already extraordinarily difficult. Returning from Mars is far more difficult, and the challenge is not purely technological. It is also logistical, economic, and deeply practical in ways that become more severe with every additional requirement added to the mission. Every critical system demands backups. Every backup requires supervision and maintenance. Every possible failure scenario requires a contingency strategy. The overall mission architecture grows exponentially more complicated with each new layer of protection, and complexity itself becomes the enemy of reliability. The more systems you introduce, the more interactions and connection points exist, and every connection creates another possible failure point. On Mars, a single failure can mean death. Engineers attempt to reduce those risks through meticulous design and testing. Components are evaluated inside Mars simulation chambers, where they are exposed to freezing temperatures, low atmospheric pressure, abrasive dust, and radiation. Critical systems are built with redundancy. 2 reactors instead of 1. Multiple pumps instead of a single pump. Backup sensors, backup controllers, backup electrical systems. Engineers also design systems to degrade gracefully, meaning that the loss of one component lowers performance without immediately triggering catastrophic collapse. But testing on Earth has limits. Scientists can imitate Martian conditions, yet they can never reproduce them perfectly. The dust on Mars is much finer, much sharper, and far more abrasive than ordinary dust found anywhere on Earth. Mars has a completely different atmosphere. Its gravity behaves differently. The radiation conditions are far harsher and more unpredictable than anything that can truly be recreated inside a laboratory or testing facility on Earth. There are realities you simply cannot understand until machinery is operating directly on the Martian surface itself. And by the time those lessons are finally learned, the first crew may already be beyond rescue. Because of that danger, some mission designers have suggested another strategy. Instead of relying on a single fuel production system, they propose sending several independent fuel generation units aboard separate cargo launches. If one system breaks down, the remaining units could continue operating. They could even be landed in different regions, so that one severe dust storm or localized environmental disaster would not disable every system at once. Fuel production could begin years before any astronauts depart from Earth, allowing engineers enough time to detect failures and attempt repairs remotely. Massive reserves of fuel could be accumulated, far beyond the bare minimum necessary, creating safety margins for inefficiencies, accidents, or unforeseen complications. But every additional cargo launch raises the cost dramatically. Every extra fuel processing plant increases the amount of mass that must be launched from Earth and safely delivered onto the Martian surface. The expenses begin to multiply rapidly. A mission estimated at $50 billion with a single fuel plant could easily rise to $70 or even $80 billion if three separate systems are operating simultaneously. And that funding has to originate somewhere. It comes from taxpayers, government spending, and resources that might otherwise be directed toward entirely different priorities. Eventually, society has to confront a difficult question. Is humanity willing to spend such staggering amounts for a mission designed to return home when a permanent one-way settlement could be accomplished for far less? Consider the Apollo program for a moment. Between 1960 and 1973, the United States invested approximately $25.8 billion to place 12 astronauts on the moon. Adjusted for inflation, that equals roughly $280 billion today. And what did that achieve? 12 individuals walking on the lunar surface for a combined total of about 9 days across 6 separate missions, with no single mission lasting longer than 1 through days from launch until splashdown back on Earth. The scale of Apollo is almost impossible to fully appreciate today. At its height in 1966, more than 400,000 people were involved with the program either directly or indirectly. NASA's budget consumed over 4% of the entire federal budget, something nearly unimaginable in the modern era, when NASA receives less than half of 1%. The Saturn V rocket, which remains the most powerful rocket ever successfully flown to completion, demanded entirely new factories and manufacturing systems. The vehicle assembly building at Kennedy Space Center, where those rockets were constructed, is still one of the largest buildings on Earth by volume. Communication infrastructure had to be established across remote islands in both the Pacific and Atlantic Oceans, so engineers could remain in contact with astronauts during lunar operations. The computational challenges, navigation requirements, and medical uncertainties were overwhelming. This happened before modern computing and before software engineering existed in the form we know today. Doctors and engineers had to invent entirely new medical procedures for living and working in zero gravity while reducing every unnecessary gram of weight. Life support systems needed to function with near-perfect reliability. 12 astronauts spending roughly 9 days total on the moon translated into about 2,000 person-hours inside the lunar module environment, along with thousands more person-hours spent in the command module during transit. Carbon dioxide had to be continuously removed from the cabin atmosphere using lithium hydroxide canisters. Water usage had to be controlled carefully because every drop mattered. Temperatures needed constant regulation in an environment where surfaces exposed to sunlight reached 127 degrees Celsius, while shaded areas plunged to minus 173 degrees Celsius. Then Apollo 13 revealed how fragile everything truly was. When an oxygen tank exploded and crippled the command module, the astronauts were forced to retreat into the lunar module, a vehicle originally intended to sustain 2 people for 2 days. Instead, it had to keep 3 people alive for 4 days. They survived only through extraordinary improvisation, constructing makeshift carbon dioxide filters with duct tape and plastic bags, shutting down nearly every electrical system to preserve power, and enduring freezing cabin temperatures after the heaters were disabled. Their survival remains one of the greatest demonstrations of engineering, creativity, and human determination ever witnessed. And remember, all of that effort, all of that money, all of that danger existed for journeys to the moon, a destination only 3 days away from Earth. The moon has no atmosphere to complicate landings. Its gravity is only 1/6 that of Earth, making launches and departures far easier. Communication delays are measured in seconds rather than minutes. Earth is always visible in the lunar sky, constantly reminding astronauts that home is nearby. If a serious medical emergency occurred on the moon, astronauts could return to Earth orbit within about 3 days and reach a hospital within 4. That timeline is incredibly demanding, but still within the limits of survival. If a major system malfunctioned, the crew could immediately cancel the mission and return to Earth. Apollo 13 demonstrated that possibility. But a complete Mars round-trip mission would be vastly more expensive and far more complicated. You would require much larger spacecraft to handle the extended voyage, greater quantities of supplies, additional backup systems, expanded life support capabilities, and far more redundancy. Instead of a mission lasting 1 week, the duration becomes roughly 3 years. Instead of placing 3 astronauts inside a capsule comparable in size to a van, you would need a crew of 6 to 8 people living inside a habitat spacious enough to preserve their mental stability during that enormous stretch of time. Rather than relying only on stored resources, the mission would need regenerative life support systems capable of recycling both water and breathable air for years at a time. Instead of basic batteries and fuel cells supplying electricity, the mission would depend on nuclear reactors or enormous solar panel systems. And instead of using a single lunar lander, the mission would require descent vehicles, long-term surface habitats, rovers, ascent vehicles, fuel manufacturing facilities, and all the supporting infrastructure needed to keep them functioning. The differences in mass are almost difficult to comprehend. The combined Apollo Command and Service Module weighed approximately 32 metric tons. A fully equipped Mars transfer vehicle could weigh several hundred metric tons. The lunar module weighed close to 15 metric tons. A Mars landing craft carrying a habitat could weigh 100 metric tons or even more. Every part of the system becomes larger. Greater mass means more fuel is required to launch from Earth. More fuel demands larger rockets. Larger rockets cost dramatically more to design, manufacture, and operate. The expenses increase at every single level. And beyond that, you would also need fuel production systems on Mars itself, an ascent vehicle capable of leaving the Martian surface, and reliable equipment to keep the entire operation functioning during the 1.5 years the crew would remain on Mars waiting for another launch opportunity. Because once you arrive there, you cannot simply depart whenever you choose. Just as the journey to Mars depends on Earth and Mars being correctly positioned, the return trip also depends on orbital alignment. If astronauts land on Mars immediately after the return window closes, they would remain stranded there for more than 2 years before another opportunity appears. Earth and Mars align favorably for interplanetary missions only once every 26 months. If the crew arrives slightly too late and misses the best departure period, they must wait roughly 26 months for the next chance. There is no shortcut around this reality. Orbital missions, or, in the best-case scenario, a small network of connected habitats. You may step outside, but only while sealed inside a spacesuit that is heavy, uncomfortable, hot, and restrictive. You cannot feel wind against your skin. You cannot smell flowers, forests, or rain. You cannot casually walk through nature. Every experience becomes mediated through machines and protective systems. Research already shows that crews living in isolated and confined conditions begin suffering substantial psychological stress after approximately 6 months. Minor habits that once seemed harmless become unbearable. Depression becomes increasingly common. Sleep cycles start to collapse. Cognitive performance gradually weakens. These effects accumulate slowly until people are no longer operating at their full mental capacity. Physical health also declines. Mars possesses only 38% of Earth's gravity. Bones no longer need to support the same amount of weight, and muscles are not forced to work as intensely. Even with demanding exercise routines, bone density decreases and muscles weaken over time. Astronauts aboard the International Space Station, where gravity is essentially absent, lose roughly 1 to 2% of their bone mass every month, despite exercising for 2 hours daily. Mars would slow the process somewhat because gravity still exists there, but the deterioration would remain serious. After 2 years, an astronaut could lose 30% of their bone density, dramatically increasing the risk of fractures and possibly creating long-term chronic pain. Medical emergencies become another continuous danger. Imagine someone developing appendicitis. On Earth, it is considered a routine surgery with relatively low risk. On Mars, where there is no hospital, no operating theatre, no anesthesiologist, and no blood bank, the situation suddenly becomes potentially fatal. You could train one member of the crew as a physician and provide surgical equipment and medical supplies, but one doctor is not the same as an entire surgical team. Complex procedures require multiple specialists with different expertise: a dentist, a radiologist, an anesthesiologist, a surgical nurse. You cannot realistically fit every one of those professions into a crew of 6 to 8 people, while also ensuring the mission includes engineers, pilots, geologists, biologists, chemists, and every other expert required to survive and operate on Mars. Telemedicine would provide some assistance. A doctor on Mars could communicate with specialists on Earth through video calls and receive advice during medical procedures. But the communication delay creates another enormous problem. When Mars is farthest from Earth, a round-trip message delay can reach 20 minutes. You cannot depend on real-time guidance during surgery if instructions arrive 10 minutes after the moment you needed them. Medical procedures would have to rely on pre-recorded training material, carefully prepared instructions written long before the mission began, and the judgment of the crew in the moment itself. The physician would be almost completely isolated, forced to make choices that could determine whether another crew member lives or dies, without any immediate assistance from Earth. Radiation exposure keeps building without pause during those 2 years on the Martian surface. Cosmic rays move through the thin atmosphere of Mars and strike the ground continuously. Spending a single year on Mars exposes a person to roughly 240 millisieverts of radiation, while people on Earth receive only about 3 millisieverts annually at the surface. The elevated cancer risk is serious, though it would not kill someone instantly. It is a long-term consequence that may take decades before appearing. But the exposure keeps accumulating. Every day spent on Mars increases the total lifetime dose. Every hour outside the habitat in a spacesuit where protection is limited adds even more exposure. By the time the astronauts finally return to Earth, if they make it back at all, they will have absorbed radiation levels that NASA's present safety regulations would never approve for any current mission. Those safety standards were created for a reason. Research involving survivors of atomic bomb explosions, patients treated with radiation therapy, victims of nuclear disasters, and astronauts who have spent extended periods in space all reveal the same pattern between radiation exposure and cancer incidence. The evidence is undeniable. Higher radiation exposure leads to greater cancer risk. For a mission to Mars, planners would need to accept dangers far beyond what any previous human spaceflight program has allowed. They would need to claim that the value of the mission justifies the greater likelihood that astronauts could later develop cancer in their lives. Some people would argue that astronauts should have the freedom to make that decision for themselves, knowingly accepting the danger involved. Others would insist that exposing humans to such intense radiation is unethical, no matter how willing the participants may be. And all of these discussions assume that things proceed relatively smoothly. No catastrophic equipment malfunctions, no sudden medical crises, no severe psychological collapse, no deadly accidents during work on the surface. Yet, Murphy's Law applies on Mars exactly as it does on Earth. Given enough time, anything capable of failing eventually will fail. And 2 years is an incredibly long time. The habitat itself could begin leaking. Tiny micrometeorites, particles moving at extreme speeds, constantly strike Mars. Unlike Earth, the Martian atmosphere is far too thin to burn most of them away before impact. A micrometeorite collision could pierce the wall of the habitat. If the opening is very small, only a few millimeters across, the crew might detect the slow loss of air in time to repair it before the pressure becomes dangerously low. But if the breach is larger, the habitat could lose pressure within minutes. The astronauts would have to seal themselves inside spacesuits, locate the leak, and potentially repair it from outside, all while handling the panic and stress of an emergency that could kill everyone involved. Or perhaps a critical life support system stops functioning. The oxygen generator shuts down, the water recycling system becomes blocked, the carbon dioxide scrubbers reach saturation. Every one of those failures starts a countdown toward death. Without oxygen, survival is measured in minutes. Without water, only days remain. Without removing CO2, the crew would have hours to days depending on the number of people inside and the amount of breathable volume available. Redundancy can reduce the danger. Backup systems are carried. Spare components are included. Multiple methods are designed for handling essential operations. But every additional backup increases both mass and cost. And even with redundancy, simultaneous failures of two systems could still become disastrous. The astronauts would need extraordinary ingenuity. They would need to identify problems using limited diagnostic equipment, repair machinery using whatever materials they have available, and improvise solutions when the correct replacement parts do not exist. They would have to remain inventive, cooperate under enormous pressure, and stay calm while human lives depend on their decisions. These are the same qualities that help save the Apollo 13 astronauts: improvisation, persistence, and the ability to solve life-threatening problems with restricted resources. But Apollo 13 lasted under a week. A Mars expedition would continue for years. The crew would have to sustain that same level of focus and competence every day, every month, throughout the entire mission. And during all of this, they would still be enduring bone deterioration, muscle loss, radiation exposure, isolation, confinement, and the constant understanding that any possible assistance is at least 6 to 9 months away. If something catastrophic happens, if the habitat is destroyed, if several crew members die, if a powerful solar flare floods the region with deadly radiation, there will be no rescue mission arriving to save them. Earth could send messages of sympathy and perhaps dispatch a memorial expedition years later to investigate what happened, but nobody would be coming in time to help. The crew would be completely alone in a way no explorers in all of human history have ever experienced before. Then, after those 2 years pass, if every system has operated perfectly, if the fuel has been successfully produced, if the ascent vehicle still works correctly, the astronauts would climb inside, launch from the Martian surface, and begin yet another 6 to 9 month voyage back toward Earth. Another 6 months traveling through space. Another extended period cut off from Earth, living in confinement, hoping every critical system continues working properly. The full mission would last close to 3 years. 36 months from the moment they depart Earth orbit until the day they splash down into the Pacific Ocean or touch down somewhere in a remote desert on Earth. 3 complete years devoted entirely to a single mission. And if they make it back, assuming they survive the return journey, their challenges still wouldn't be over. They would spend months recovering physically. Their bones would have lost density. Their muscles would have weakened from prolonged exposure to low gravity. Their cardiovascular systems would have adapted to Mars and microgravity conditions and would need time to function properly again under Earth's 1G environment. Extensive rehabilitation would almost certainly follow. Physical therapy would be unavoidable. Some astronauts might even require surgery to repair long-term damage caused by the mission. There would also be continuous medical observation for the rest of their lives, especially to monitor possible radiation-related cancers caused by years in deep space. The first crew to reach Mars would not only return as heroes, in many ways, they would also return as long-term medical subjects, living evidence of what extended deep space travel does to the human body over multiple years. So the real question becomes, is it worth it? That depends entirely on human priorities and values. What is the true value of landing a small group of people on Mars, allowing them to remain there for roughly 2 years, and eventually bringing them home again? What discoveries could humans make there that robotic explorers could not? What meaning exists in placing a flag into Martian soil and leaving human footprints behind? What kind of inspiration could such a moment give to generations that come after us? Scientifically, the argument for human missions is not especially strong. Robots are already capable of doing much of the work humans would perform on Mars, and they accomplish it without life support systems, without return vehicles, and without risking human lives. Rovers such as Perseverance and Curiosity can spend years studying rock formations, drilling into the surface, collecting data, and searching for traces of ancient microbial life. They never become exhausted. They don't require oxygen, food, or water. Radiation does not frighten them. For the cost of sending one human crew to Mars, multiple robotic missions could be launched instead. And if one robot stops functioning, the loss is disappointing, but not catastrophic. No families lose loved ones. Another machine can simply be sent later. Humans, however, still possess important advantages. They are flexible and adaptable. They can make complicated decisions instantly. They can solve unexpected problems creatively in ways current machines simply cannot replicate. A trained geologist standing directly on the Martian surface could immediately recognize unusual terrain, investigate it without delay, and alter research plans based on new discoveries. Robots cannot work that way. They depend on commands transmitted from Earth, and by the time instructions arrive and are carried out, the environment may already have changed completely. Human astronauts could also perform sophisticated repairs and technical tasks that modern robots would struggle to accomplish. But the central debate remains unchanged. Are those human advantages worth spending hundreds of billions of dollars while accepting a serious possibility that crew members may die? The discussion has never truly ended. Some people believe exploration is inseparable from being human itself. They argue that crossing boundaries and entering the unknown is part of our nature, that humanity should travel to Mars for the same reasons explorers once climbed Everest or sailed toward Antarctica. Because it exists. Because humanity is capable of doing it. Because refusing to go feels like abandoning something fundamental inside the human spirit itself. Others strongly disagree. They see that argument as emotional romanticism rather than responsible policy. Space agency budgets are finite. The enormous cost of a human Mars mission could instead support dozens of robotic missions to Mars, the moons orbiting Jupiter and Saturn, distant asteroids, comets, and advanced telescopes searching for Earth-like planets around other stars. From a scientific perspective, robots provide greater returns for each dollar spent. According to this view, decisions should be guided by evidence and efficiency rather than emotion. Planting flags and leaving footprints may inspire people, but critics argue those symbolic achievements are not worth risking human lives or spending vast sums that could instead address urgent problems on Earth. But what happens if the astronauts are never expected to return at all? A one-way mission to Mars changes everything. Suddenly, many of the most difficult mission requirements disappear. There is no need for a launch vehicle capable of leaving Mars. No need for massive fuel production systems on the Martian surface. No need to remain there for 2 years waiting for the correct return launch window. No requirement to carry supplies for another 6 to 9 month journey back to Earth. The entire mission becomes less complicated, less expensive, and in certain ways even safer. You send the crew to Mars. They land successfully, they move into a permanent habitat, and continue living there indefinitely. They become the first permanent human settlers on another planet, the first true Martian colonists. But it is important to fully understand what one way really means. This is not merely a technical adjustment to mission planning, it completely changes the human meaning of the mission itself. You are no longer asking astronauts to spend 3 years traveling to Mars and returning home. You are asking them to leave Earth permanently. You are asking them to accept that they will never again walk beside an ocean, never swim in open water, never wander through forests, never stand beneath falling rain, never smell flowers after a storm, never sit together with family during holidays, never revisit the streets and places where they spent their childhood. Every farewell becomes permanent. Every final glance at Earth through the spacecraft window truly is the last one. There are no change decisions later, no emergency return flights, no second opportunities, no coming back home. And this idea is not hypothetical. It has already been proposed before. In 2012, a private organization called Mars One, created by Bas Lansdorp in the Netherlands, suggested exactly this kind of mission. The proposal involved sending volunteers on a permanent one-way mission to Mars, creating a lasting settlement that would receive periodic supplies from Earth, but would never return its inhabitants home. It was a bold concept, Perhaps too bold for reality, their strategy for financing the project relied on reality television, turning the entire process into a global media event. The candidate selection, the years of preparation, the voyage through space, the landing on Mars, every stage would be broadcast as entertainment. Hundreds of millions of people around the world would watch ordinary individuals transform into the first true Martians, while advertising profits would supposedly finance future missions. The public reaction was extraordinary. Mars One received more than 200,000 applications from individuals across over 140 countries, including teachers, engineers, students, military veterans, physicians, artists, and people from nearly every imaginable profession, culture, and age group. Some applicants were highly trained scientists with PhDs and qualifications that made them suitable candidates on paper. Others had absolutely no relevant experience, but were eager to study and adapt. What united all of them was the willingness to abandon their entire lives for the opportunity to participate in something historic. In the end, the project collapsed. Financial difficulties kept growing. The technological obstacles turned out to be far more severe than expected. Serious doubts emerged about whether the organization possessed the expertise, infrastructure, and resources necessary to accomplish something so extraordinarily complicated. By 2019, Mars One officially declared bankruptcy. The company had failed to raise anything close to the billions of dollars required. They had created promotional campaigns and attracted massive media attention, but no actual spacecraft hardware had been built, no launch agreements had been secured, and none of the essential systems needed to keep humans alive on Mars permanently had been completed. Yet the fact that 200,000 people still volunteered reveals something profound about human beings. People are willing to accept tremendous danger and life-altering sacrifice for causes they truly believe in, for the possibility of participating in history, for the chance to matter in a way that reaches beyond ordinary existence. The psychological screening for such a mission would have to be extremely demanding. The preparation period would last for years. Every risk would be explained in complete detail. Applicants would be directly informed that they were choosing to spend the remainder of their lives on Mars, that there would be no rescue mission, no emergency evacuation, no opportunity to reverse the decision once the spacecraft launched. And still, thousands of capable people would continue applying. Human history is filled with similar decisions. The pilgrims who crossed the Atlantic aboard the Mayflower in 1620 understood that they would most likely never see England again. Death rates were devastatingly high, yet more people kept coming, motivated by religious liberty, economic possibilities, or simply the hope of beginning a different life. The pioneers who traveled the Oregon Trail during the 1800s endured journeys lasting many months through harsh and dangerous territory, abandoning everything familiar behind them. Many never survived the trip. Ernest Shackleton's famous advertisement for his Antarctic expedition in 1914 declared, "Men wanted for hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return, doubtful, honor and recognition in case of success." More than 5,000 people applied for only 28 available positions. They understood the danger completely. They still chose to go. The first settlers on Mars would belong to that same tradition. They would not be tourists visiting another planet for adventure. They would be pioneers, exchanging their former lives for a permanent future on an entirely different world. They would fully understand the risks involved. They would willingly accept them. For years, they would train in geology, engineering, medicine, spacecraft operations, agriculture, and every other skill that might become necessary for survival. They would say farewell to family and friends through a series of emotionally painful goodbyes, where everyone involved understands that the separation is permanent. They would enter the spacecraft knowing they are leaving Earth forever. Psychological readiness would become one of the most important aspects of the mission. Technical ability alone would never be enough. The mission would require people capable of enduring extreme isolation, confinement, pressure, and the constant awareness that they are completely on their own. Psychiatric evaluations would search for candidates vulnerable to depression, anxiety, or other mental health conditions that might become overwhelming in the Martian environment. Mission planners would look for emotional stability, resilience under stress, and the ability to continue functioning while afraid, exhausted, or uncertain. They would also need people with strong interpersonal abilities, individuals capable of resolving conflict calmly instead of allowing resentment to grow over time. The chemistry within the group would be examined with enormous care. A crew of 6 to 8 individuals living together for years must be deeply compatible. They would need to trust one another, cooperate effectively, and support each other emotionally during difficult periods. A single destructive personality could damage the morale and stability of the entire mission. Research conducted in Antarctic bases, submarines, and aboard the International Space Station consistently shows that interpersonal conflict becomes one of the greatest threats in isolated environments. Minor annoyances can slowly grow into serious problems over long periods of isolation. The way a person eats, their cleanliness habits, how they approach work, even the kind of jokes they make, any of these could eventually create tension when there's no opportunity to leave or spend time apart. The crew would require a powerful shared mission, something capable of uniting them and giving purpose to the hardships they endure. This helps explain why many early settlers throughout history were deeply religious or strongly driven by ideology. Their beliefs allowed them to see suffering as meaningful instead of meaningless. Future Mars settlers may not necessarily follow religion, but they would still need an equivalent source of motivation. They would need a profound belief in the value of building a human presence on Mars, confidence that they are helping secure humanity's long-term future, and the conviction that their personal sacrifices could allow future generations to live across multiple planets. Preparation for such a mission would take years, perhaps anywhere from 5 to 10 years, depending on the experience and education of the candidates. They would need to learn an enormous variety of abilities, basic medical knowledge ranging from treating fractures to carrying out surgical procedures, engineering expertise advanced enough to repair or improvise solutions for nearly every critical system inside the habitat, agricultural training focused on producing food inside Martian greenhouses, geological skills for recognizing valuable samples and carrying out scientific fieldwork, piloting experience for controlling rovers and drones, construction methods for enlarging habitats using Martian resources. Their training would happen in Mars, analog environments, isolated regions on Earth designed to imitate certain Martian conditions. Places such as the Mars Desert Research Station in Utah, the Flashline Mars Arctic Research Station in the Canadian Arctic, volcanic terrain in Iceland, and high-altitude desert areas in Chile. They would spend months living in these remote environments, staying inside simulated habitats, stepping outdoors only while wearing imitation spacesuits, eating food intended to resemble future Mars meals, and coping with staged equipment malfunctions. These experiences would provide a partial understanding of what existence on Mars could feel like, although no place on Earth can truly reproduce the combination of a thin atmosphere, reduced gravity, intense cold, and radiation exposure that makes Mars unique. Psychological care would remain essential during training and after arrival on Mars. There would be regular counseling sessions, group discussions, and constant observation for warning signs of mental health decline. Once on Mars, the crew would still be able to communicate with therapists on Earth through telecounseling, although communication delays would severely reduce its usefulness. A real-time therapy conversation becomes impossible when every interaction requires 20 to 40 minutes for a complete exchange. Instead, astronauts would send recordings or written updates. Therapists would examine them and reply with guidance or perspective, and the crew would receive those responses hours later. It would still help, but it could never fully replace direct human support. The first expedition would probably remain very small, perhaps 4 to 6 astronauts in the initial crew. Their habitat would already be waiting for them, delivered to Mars months or even years before the crew arrived and thoroughly tested in advance. Automated systems would unfold solar arrays, prepare airlocks, and confirm that life support systems were operating correctly. Their spacecraft would land nearby, close enough that the astronauts could walk to the habitat within an hour or two while wearing spacesuits, but distant enough to prevent landing debris from damaging the existing structures. The opening weeks would be extremely important. Equipment would need to be unloaded from the spacecraft and transferred into the habitat. Backup systems would need to be installed. Every system would require repeated testing. The crew would establish routines for daily survival, maintenance work, and scientific operations. At the same time, they would begin adapting psychologically to the reality of permanent life on another planet. At first, excitement and novelty would help carry them forward. Everything would feel extraordinary. They would be standing on Mars. They would be making history. They would become the first human beings ever to live on another world. But after several months, the emotional reality would begin to settle in. This would no longer feel like an adventure. It would simply become normal life. The same habitat every day, the same narrow rooms, the same people, the same meals, the same repetitive schedule. Mars itself rarely changes. The horizon looks almost identical from one day to the next and will continue looking that way tomorrow. The sky remains that familiar butterscotch pink. The sun always appears small and remote. The rocks always carry that rust-colored appearance. Mars does not experience seasons the way Earth does. Instead, there are only slow temperature variations as the planet circles the sun. Work would become essential for maintaining purpose and structure. Scientific exploration is the central reason for establishing humans on Mars in the first place. The crew would perform geological surveys, gather rock and soil samples, search for traces of ancient microbial life, examine Martian weather patterns, and test technologies intended for future settlers. They would install scientific instruments, repair equipment, record discoveries, and transmit data back to Earth. Researchers on Earth would study the information, send questions, request additional experiments, and continue collaborating across millions of kilometers of distance. Agriculture would also demand enormous amounts of time and concentration. Producing food on Mars is critical for achieving long-term independence and survival. The greenhouses would operate under pressure using a carefully balanced mix of nitrogen and oxygen, maintained at temperatures comfortable for humans, and illuminated by LED systems adjusted to the wavelengths most effective for photosynthesis. The settlers would likely cultivate rapidly growing crops such as lettuce, spinach, radishes, tomatoes, and perhaps potatoes, which provide significant calories while surviving in relatively low-quality soil. If enough greenhouse space existed, they might also grow rice or wheat, although grains require more time to mature and generally produce fewer calories per square meter compared with vegetables. The growing medium would consist of Martian regolith that had been treated to remove toxic perchlorates and enriched with organic material created from processed human waste. Composting toilet systems would recycle biological matter, though the entire process would demand strict oversight to prevent dangerous pathogens from spreading. Water would be obtained from melted Martian ice, then purified and continuously recycled through the colony's life support infrastructure. At first, nutrients would come from reserves transported from Earth, but over time the settlement would eventually need to become completely self-sustaining, extracting everything necessary from Martian materials and resources. Agricultural failure would represent one of the colony's greatest dangers. If disease destroyed the greenhouse crops, if a pressure seal failed and the plants froze, or if lighting systems malfunctioned and deprived the crops of sufficient illumination, the colonists could face the real possibility of starvation. Emergency food reserves would exist in the form of freeze-dried meals and preserved supplies shipped from Earth, but those reserves would always be limited. If several growing cycles failed consecutively, strict food rationing would become unavoidable while they waited for the next supply mission from Earth, hoping it arrived before every remaining resource was exhausted. Maintenance would never truly stop. Spacesuits would gradually develop punctures and worn seams. Air recycling equipment would become clogged with fine dust. Water purification systems would slowly collect mineral buildup. Solar panels would be coated with Martian dust and require regular cleaning. Batteries would deteriorate with age. Every machine and system would possess a limited operational lifespan before eventually breaking down. The settlers would need machine shops stocked with equipment, spare components, and raw materials capable of producing replacement parts. More importantly, they would need the intelligence and creativity required to keep systems functioning long beyond their intended design limits. This is one of the major reasons humans provide capabilities that robots alone cannot replace. A human engineer can inspect a damaged pump, identify the point of failure, and invent an alternative solution using whatever materials remain available. They can cannibalize components from one system to repair another. They can improvise fixes no engineer on Earth could have predicted while originally designing the equipment. The crew of Apollo 13 survived because of precisely this kind of creative improvisation. A Martian colony would require those same abilities continuously for years instead of only a few days. The colony's social structure would likely develop naturally over time. In a group of 6 people, there is little room for an inflexible chain of command. Every individual would need to contribute. Every skill set would matter. Every opinion would carry importance. Decisions would probably rely heavily on consensus, with the crew debating issues together and reaching agreements collectively rather than simply following direct orders from a commander. Naturally, emergencies would still require someone capable of making rapid decisions, so a mission leader would likely be assigned authority during crises. But in ordinary daily life, collaborative leadership would help strengthen morale and ensure everyone remained invested in the colony's success. Celebrations and rituals would become essential for tracking time and preserving psychological stability. Birthdays, anniversaries of their arrival on Mars, and holidays from their home cultures would all carry deep emotional significance. Over time, the settlers might even create entirely new Martian traditions to honor important milestones in the colony's development. The first successful greenhouse harvest. The first child born on Mars, assuming the settlement eventually became large enough. The first exploration of a previously unvisited region. Conflict, however, would be unavoidable. Place 6 human beings together inside a confined environment for years, and eventually they will irritate one another. Arguments would emerge over task priorities, unequal workloads, allocation of scarce resources, or disagreements between scientific goals and immediate survival needs. Minor frustrations can grow dangerously when there is nowhere to escape. Someone who refuses to clean shared kitchen spaces properly, someone who creates excessive noise during designated sleep hours, someone who dominates communication time with Earth while bandwidth remains limited. Because of this, the crew would need strong conflict resolution abilities, learning how to confront problems honestly but respectfully, express frustration without making personal attacks, forgive smaller mistakes instead of nurturing resentment, and compromise whenever total agreement proves impossible. They would probably hold regular group discussions where grievances could be openly addressed before tensions escalated into something more serious. Physical intimacy would create another complicated challenge. Would romantic relationships eventually form among the crew? Almost certainly. If the mission includes both men and women, no amount of training or psychological screening can completely eliminate natural human attraction. Human beings will inevitably develop emotional connections with one another, including romantic relationships. The real challenge is figuring out how to manage those connections without allowing jealousy, favoritism, or personal conflict to damage the stability of the group. Some mission designers have proposed selecting married couples or long-term partners, people who have already maintained committed relationships for many years. Others believe that even strong relationships on Earth may not survive the extreme psychological pressure of living on Mars, and that a breakup inside a confined habitat could severely damage morale and cooperation among the crew. Pregnancy during the earliest missions would create enormous problems, not because having children on Mars is fundamentally undesirable, but because the first settlers simply would not be equipped to handle childbirth or raising children safely. They would not have obstetricians, pediatric specialists, or neonatal intensive care facilities. Pregnancy under low gravity conditions combined with continuous radiation exposure introduces risks nobody fully understands yet. Human development could proceed differently. Birth complications that are routine and manageable on Earth might become dangerous on Mars. And even if everything during delivery proceeded successfully, caring for an infant inside a pressurized habitat while simultaneously conducting scientific work and maintaining life support systems would push the crew far beyond what they could realistically manage. Future missions, after the settlement becomes larger and more stable, could eventually include families. Children would be born and raised on Mars, growing up with the planet as the only true home they have ever known. Earth would exist for them mostly through photographs, recordings, and stories told by older generations. They would look toward Earth in the night sky, bright enough at closest approach to cast faint shadows, and try to picture oceans, forests, cities, and billions of human beings. But those ideas would feel distant and abstract. Mars would be tangible and immediate. The reddish soil, the freezing thin atmosphere, the repetitive rhythms of daily existence inside a pressurized dome would define normal life. Those children might never have the ability to visit Earth at all. Growing up in 38% gravity would shape their bodies differently from humans raised on Earth. Their bones and muscles would adapt to Martian conditions. Transitioning to Earth's 1G environment could become physiologically impossible. They might feel nearly 3 times heavier, unable to walk properly or even stand for long periods, while their cardiovascular systems struggled to circulate blood under stronger gravity. In every meaningful way, they would become Martians, biologically adjusted to their own world, and incapable of surviving comfortably on the planet where humanity originally evolved. But to them, that would not feel tragic. Earth would seem like the strange and foreign place. Mars would feel ordinary. They would study Martian geology, Martian geography, and eventually Martian history in school. They would learn about the first settlers who arrived from Earth and chose to remain permanently. They would hear stories about the difficult years spent constructing the earliest permanent habitats. They would study the gradual growth of the colony as new missions continued arriving over time. Slowly, a distinct Martian culture would emerge, influenced by Earth but no longer identical to it. Culture itself would likely transform in ways nobody can fully predict. Language could evolve. Colonists might invent entirely new words to describe uniquely Martian experiences and environmental conditions that have no equivalent on Earth. Slang would naturally emerge from shared hardships and daily routines. Over generations, even grammar might begin to shift as Martian-born children grow up hearing Earth languages used in completely new branch of civilization far from humanity's birthplace. Eventually, some form of political system would become unavoidable. The first crews would operate under the authority of the organizations that launched them, whether NASA, SpaceX, or an alliance of international space agencies. But once the colony expands and second or third generation Martians begin to exist, questions about governance could no longer be ignored. Who holds authority? Who creates and enforces laws? How are disagreements settled? Do Martian settlers possess independent rights? Do they remain loyal to governments on Earth? Or do they become self-governing? These questions may sound far away, yet history repeatedly demonstrates that colonies tend to pursue independence sooner or later. The American colonies separated from Britain, Australia transformed from a penal colony into an independent nation. Even Antarctica, despite being regulated through international agreements, still faces ongoing arguments over sovereignty and resource ownership. Mars would probably follow a similar path, except much faster, because the physical distance between Mars and Earth is vastly greater. Earth would have no practical way to send military forces to control Mars. The voyage requires too much time, too many resources, and too much international coordination. By the time any punitive mission reached Mars, the entire political situation might already be completely different. A Martian declaration of independence could happen decades or centuries after the initial landing. Or it might occur surprisingly early, if the settlers believe Earth is treating them as expendable property instead of autonomous human beings. Imagine a situation where Mission Control on Earth orders Martian colonists to endanger their lives for a scientific objective that feels unnecessary or irrational to the people actually living there. Would the settlers obey simply because Earth claims authority? Or would they reject the order and insist on making decisions regarding their own survival and safety? The communication delay itself would give Mars a significant advantage in any disagreement. Earth could transmit commands, but Mars would still have 20 to 40 minutes before even learning how Earth reacted to their previous decisions. By the time communications travel back and forth between the two planets, circumstances may have already changed completely. Mars could present Earth with fate's accomplice, decisions and actions already carried out before anyone on Earth even has time to respond or object. That imbalance in communication delays changes the structure of power itself. Control becomes far more difficult when instructions arrive minutes or even hours too late to matter. The economic connection between Earth and Mars would also become increasingly complicated. The earliest missions would almost certainly be financed by governments or private organizations on Earth, expecting some kind of return on their investment. That return could come in the form of scientific discoveries, broadcasting rights, international prestige, or strategic advantages tied to future resource extraction. But eventually, a deeper question emerges. What happens once Mars no longer depends on Earth to survive? What happens when settlers can grow their own food, build their own equipment, and maintain their civilization without constant shipments from Earth? At that point, the justification for continuing financial support becomes far less clear. Mars contains resources that Earth could theoretically value greatly: massive reserves of water, ice, mineral deposits, including materials that may contain rare Earth elements. Deuterium, the hydrogen isotope that could become important if fusion energy ever becomes practical on a large scale. Carbon dioxide useful for industrial manufacturing. Iron oxide, the reddish dust covering the planet, which could be refined into iron and oxygen. Yet harvesting those materials and transporting them back to Earth would require gigantic amounts of infrastructure and energy. In reality, obtaining those same resources from asteroids or even the Moon would almost certainly be cheaper and more efficient because they are much closer and have weaker gravity, making launches far easier. The true importance of Mars may ultimately be strategic rather than commercial. It represents a second home for human civilization, a safeguard against catastrophes centered on Earth. It could serve as a launching point for missions deeper into the solar system, positioned closer to the asteroid belt and the moons orbiting Jupiter and Saturn. It could become a scientific center for studying planetary evolution, astrobiology, and the long-term biological effects of reduced gravity and intense radiation on human beings. None of these goals produce profit in the traditional sense, but they still create enormous value worthy of long-term investment. As years pass, the colony would slowly become increasingly independent, needing less and less support from Earth to survive. Every cargo shipment arriving from Earth would bring tools that increase self-reliance. 3D printers capable of manufacturing replacement parts and equipment. Heavy industrial systems designed to refine Martian ore into usable metals. Chemical facilities for producing plastics, medicines, fertilizers, and industrial compounds. Genetic archives to preserve agricultural diversity, educational systems, and learning materials for children born on Mars. Every new layer of independence would make the settlement stronger and less exposed to interruptions in supply lines. Eventually, perhaps 100 or 200 years after the first human landing, Mars could contain tens of thousands of residents. Entire cities hidden underground or protected beneath massive pressurized domes. Agricultural systems supplying most of the population's food. Factories building nearly all necessary equipment locally. Universities devoted to solving uniquely Martian problems. Spaceports launching expeditions toward the asteroid belt and the outer planets. At that stage, Mars would no longer simply be a colony. It would become a fully independent branch of human civilization, following its own path while still sharing culture, science, and communication with Earth. Now think about the enormous reduction in spacecraft mass. A vehicle intended only for a one-way mission would not need to carry fuel for the trip home. It would not need a return ascent vehicle waiting on the Martian surface. It would not require additional life support systems for months of return travel through space. All of that saved mass could instead be used for far more valuable purposes. Additional supplies for surviving on the surface, better habitat equipment, greater redundancy for critical systems, more scientific instruments, more resources dedicated entirely to helping the crew live and succeed on Mars. The financial cost would decrease enormously. Instead of requiring hundreds of billions or even $1 trillion, a one-way Mars mission might cost only tens of billions. Still extraordinarily expensive. Still one of the greatest engineering projects in history, but no longer completely beyond reach. A wealthy nation, or several nations working together, could realistically fund such a mission. In fact, humanity could probably launch a one-way mission to Mars within the next 10 to 20 years, using technology that already exists today, combined with focused technological development. No miraculous scientific breakthrough would be necessary. What would truly be required is commitment, political will, and sustained funding. But then comes the question many people ask immediately. Would anyone truly agree to go? Would human beings willingly board a spacecraft knowing they will never return to Earth? Never again breathe natural air without filters? Never again stand in falling rain? Never swim in an ocean? Never walk through a forest or feel wind across their skin? Would people accept spending the rest of their lives inside pressurized habitats and spacesuits on a freezing, lifeless planet with a poisonous atmosphere, entirely dependent on machines for every breath of air, every sip of water, every piece of food? The answer is yes. Without hesitation, people would volunteer. When Mars One announced its proposed mission, more than 200,000 people from over 140 countries submitted applications. 200,000 individuals willing to leave Earth forever for the opportunity to become part of history, to stand on another world, and to become some of the first human beings ever to call Mars home. The psychological evaluations would have to be extremely demanding. The preparation process would last for years. Every danger and possible outcome would be explained in complete detail. And still, thousands of highly capable people would volunteer. Why would they do it? Because the desire to explore is deeply woven into human nature. Because there are individuals who place discovery above comfort. Because the opportunity to become part of something greater than themselves, to help shape humanity's future, to leave behind a legacy remembered for generations, speaks to certain people in ways that ordinary safety and familiar routines never can. The people who sailed across the Atlantic to establish colonies in the Americas during the 1600s understood that they would likely never return home. The voyage itself was dangerous. The destination remained uncertain. Life waiting for them would be difficult and unforgiving. Many lost their lives, but they still went, motivated by hope, ambition, and the dream of building something entirely new. The first settlers on Mars would share that same mindset. They would not be tourists visiting another world for a short time. They would be pioneers. They would fully understand that they were exchanging their old lives on Earth for a completely different existence on another planet. They would know the dangers involved. They would willingly accept them. They would spend years preparing, say their final goodbyes to family and friends, and enter the spacecraft fully aware that Earth would never again be their home. And the remarkable part is this. Once humans are living on Mars, they would not necessarily require rescue missions. They would still need support, of course. Cargo ships arriving regularly from Earth would bring food, replacement parts, medicine, scientific equipment, and essential supplies. But evacuation would not be the objective. The settlers would adapt. Mars itself would become their new home. They would learn how to survive in that harsh environment, how to work within it, and eventually, how to flourish there. As time passed, the colony would gradually become more independent, producing more of its own food, building more of its own machinery, and depending less on Earth for everyday survival. Eventually, years or perhaps decades later, the Martian settlement could develop the ability to construct a vehicle capable of returning to Earth. By then, the colony might possess the industrial systems, fuel production facilities, and technical knowledge necessary for such an achievement. A child born on Mars, someone who had only ever seen Earth as a brilliant point of light in the sky, might one day choose to visit the original home of humanity. At that stage, the resources and technology could finally exist to make that possible. But that moment would arrive much later, only after the colony had matured, after the infrastructure had been built, after Mars had truly become humanity's second home. The first humans who travel to Mars will almost certainly not return, because returning them is not the central purpose of the mission. The true objective is to create a permanent human presence on another world, to ensure that humanity is no longer trapped on a single planet and vulnerable to every disaster that could strike Earth. An asteroid collision, a supervolcano eruption, a global pandemic, nuclear conflict, climate collapse, any one of these events could severely damage Earth's ecosystem and threaten the future of civilization itself. But if human beings are living on Mars, if self-sustaining settlements exist on multiple worlds, then humanity continues to survive. We become an interplanetary species, spreading throughout the solar system instead of placing our entire future on one fragile planet. This is the real reason humanity wants to reach Mars and remain there permanently. Not because the mission is simple, inexpensive, or safe, but because it may ultimately be necessary for long-term survival. Keeping the entire human species confined to one planet, even a world as extraordinary and life-supporting as Earth, is a risk we may eventually decide is unacceptable if we possess the ability to expand beyond it. Mars is the most practical first option for a permanent colony. It is the nearest planet with a solid surface that is not an unbearable inferno like Venus. It contains water ice that can be extracted, melted, and purified. Its atmosphere, although extremely thin, can still be processed to produce oxygen and nitrogen. A Martian day lasts 24 hours and 39 minutes, close enough to Earth's daily cycle that humans could adapt without major difficulty. Mars also experiences seasons because of its axial tilt, although those seasons last nearly twice as long as Earth's, because Mars takes more time to orbit the Sunday. The temperatures there, while brutally cold compared with Earth, are still survivable with proper insulation and heating systems. The average temperature is minus 63 degrees Celsius, but around the equator during summer, daytime temperatures can briefly climb to a pleasant 20 degrees Celsius before dropping to minus 73 degrees Celsius during the night. Low gravity, however, would create serious complications. Mars has only 38% of Earth's gravity, meaning long-term residents would likely suffer bone density reduction and muscle deterioration over time. Children born on Mars might grow differently from children raised on Earth, developing bodies adapted to weaker gravity, with lighter bones and reduced muscle strength. Some of them might never be physically capable of visiting Earth because their bodies could struggle to survive under the stronger gravitational pull, but to them, that would not matter. Mars would be the world they belonged to. Earth would feel like the strange and hostile planet, the place where gravity is overwhelmingly heavy, and every object weighs nearly 3 times more than it does on Mars. Radiation remains one of the most significant dangers. Mars lacks a global magnetic field and its atmosphere is extremely thin, which means cosmic radiation and solar particles can strike the surface with very little protection blocking them. Extended exposure would raise the likelihood of cancer and might lead to many other medical complications as well. Future settlers would have to construct living spaces with strong radiation shielding, perhaps beneath the ground or buried under thick layers of Martian regolith. They would need to minimize the amount of time spent outside in spacesuits. Constant medical supervision and treatments designed to reduce radiation damage would become part of everyday life. Yet these difficulties are manageable. Humanity already understands how radiation shielding works. We already know how to track and control exposure levels. This is ultimately an engineering problem, not an insurmountable wall. The psychological struggle could prove even more difficult than the physical dangers. Human beings evolved on Earth, surrounded by blue skies, forests, rivers, rain, birdsong, and the countless sounds of living ecosystems. Mars offers none of those comforts. During the daytime, the Martian sky appears butterscotch pink, shifting toward blue around the sun at sunset. Silent and alien. The settlers would need to invent an entirely new culture, a new society, and deeper purposes that extend beyond simple survival. They would need music, stories, paintings, and books. They would need sports, traditions, festivals, and shared rituals. They would need emotional bonds with one another and a powerful sense of meaning connected to their mission. They would have to create a community capable of surviving psychologically, not just biologically. This may become the greatest challenge of all. Not the machinery, not the transportation systems, not even the engineering. The true difficulty may lie in the human mind itself. Keeping people mentally healthy, inspired, and emotionally connected over many years in an environment fundamentally hostile to human existence. But there is also reason for optimism. Humanity is remarkably adaptable. We have established civilizations in nearly every environment on Earth, from the Arctic to the Sahara, from isolated mountain regions to tropical islands. Since the year 2000, humans have maintained a continuous presence aboard the International Space Station, living in space for more than 2 decades without interruption. We have already learned how to survive and function in places that would otherwise kill us without advanced technology. Mars would simply represent the ultimate expression of that adaptability. Difficult beyond imagination, yes. Impossible, no. The first settlers on Mars would become legendary figures. As long as human civilization survives, their names would be remembered. Children on both Earth and Mars would study their stories. They would become the Neil Armstrong and Buzz Aldrin of an entirely new era, the pioneers who carried humanity toward becoming a species that lives on more than one planet. But unlike Armstrong and Aldrin, who spent only a few hours on the moon before returning home, these colonists would remain there permanently. Mars would become the place where they lived the rest of their lives. Their bodies would eventually rest beneath Martian soil, becoming part of another world forever. And there is something strangely beautiful about that. Humanity was born on Earth, but perhaps we are capable of growing beyond it. Perhaps we can learn to adapt to unfamiliar worlds and create homes where no human being has ever existed before. The first humans to die on Mars would also become the first whose atoms never came back to Earth. Their remains would stay on another planet permanently, woven into the future of Mars itself. Their sacrifice would make every future generation of Martians possible. By choosing to leave Earth forever, they would open the path for millions, perhaps even billions, to follow after them. Future generations could build cities, farms, schools, and entire societies. Over centuries, they might even terraform Mars itself, transforming it into something closer to a second Earth, because that is the true, long-term dream. Not merely a tiny outpost where a few dozen people struggle to stay alive, but a flourishing civilization populated by millions, vast cities beneath protective domes or deep underground, linked together through tunnels and transportation networks, agricultural systems producing food, factories, manufacturing equipment and materials, universities developing new science and technology, governments, economies, traditions, and cultures unique to Mars, while still connected to humanity's origins on Earth. Reaching that future would require centuries. The first colonists would witness only the earliest stage of that transformation. They would probably spend their lives inside small habitats, underground shelters, or lava tubes designed to shield them from radiation. Every day would involve constant work, maintaining life support systems, growing food, and carrying out scientific research important enough to justify the enormous cost of supplying them from Earth. They would understand that they were building the beginning of something they would never live long enough to see completed. They would be planting seeds whose harvest belonged to distant generations. Yet they would also understand how necessary their role truly was. Someone has to go first. Someone has to demonstrate that permanent life on another world can actually work. Someone must establish that first foothold, that first lasting human presence beyond Earth. And in return, they would witness experiences unlike anything any human being in history has ever known. They would become the first human beings to witness a sunrise on Mars, where the sun appears far smaller and more distant than it does in Earth's sky. They would be the first to watch the Martian moons, Phobos and Deimos, streaking overhead across the thin atmosphere. They would stand among giant volcanoes and immense canyons before anyone else, studying the surface of Mars directly, examining its geology with their own hands, searching through stone and buried ice for traces of ancient organisms. Because there is a real possibility that Mars once supported life. Billions of years in the past, Mars was not the frozen desert we know today. The planet was warmer, wetter, and far more active. Rivers once flowed across its surface. Lakes existed there, and perhaps even a vast ocean filled the northern lowlands. Its atmosphere was thicker, and a magnetic field shielded the planet from harmful radiation. These conditions may have allowed life to appear and evolve. But eventually, something went wrong. Mars lost its magnetic field, likely because its core gradually cooled over time. Without that magnetic protection, the solar wind slowly stripped away the atmosphere. Water either froze beneath the ground or escaped into space. Over immense stretches of time, the world transformed into the cold and barren planet we see today. Yet if life once existed on ancient Mars, evidence of it may still survive. Fossils could remain trapped within sedimentary rock layers. Organic compounds might still be preserved in frozen ice deposits. There may even be dormant microbes hidden in underground aquifers if liquid water continues to exist beneath the surface. The first Mars settlers would have the chance to investigate these possibilities directly, pursuing one of the greatest scientific questions humanity has ever asked. Did life emerge independently on Mars? Or is Earth truly the only planet in the solar system that ever hosted living organisms? Discovering proof of past Martian life would completely transform our understanding of biology and humanity's place in the cosmos. It would demonstrate that life can develop whenever the conditions are right, that Earth is not some singular exception, and that countless living worlds may exist around billions of stars throughout the universe. Such a discovery would alter everything we believe about existence itself. And even if Mars turns out to have never supported life at all, the scientific value would still be extraordinary. By studying Martian geology and climate, humanity would learn how planets evolve over billions of years, how habitable worlds form, and how they eventually become uninhabitable. That knowledge could help us better understand Earth's own future, improve predictions about climate and planetary change, and guide us in identifying potentially habitable exoplanets orbiting distant stars. The scientific rewards alone would make the mission worthwhile. But the deeper reason for going to Mars is even more straightforward. Humanity would go there and remain, because it has the ability to do so. Because the alternative would mean staying on Earth forever, refusing to expand, refusing to explore, refusing to take the next step in the long evolution of our species. Human beings have always crossed boundaries. We have always wanted to know what lies beyond the next horizon, over the next mountain, across the next ocean. Now humanity can look toward another planet and ask that same timeless question. What exists there? What can we discover? Could humans survive there? The answer to that final question appears to be yes, but only with enormous dedication and sacrifice. It requires individuals willing to leave Earth permanently. It requires accepting that the first settlers on Mars would be beginning a one-way journey. They would leave behind everything familiar for the chance to participate in the greatest adventure humanity has ever attempted. They would not return home. They could not return home, not because science makes it absolutely impossible, but because the immense resources required for return missions could instead be used to send additional settlers, additional supplies, and additional machinery. Every kilogram of fuel created on Mars for a trip back to Earth would be fuel unavailable for exploration, construction, or survival. Bringing colonists back would undermine the very purpose of the mission itself, which is not simply to visit Mars, but to establish a lasting human presence there. And the colonists would understand that reality completely. They would accept it willingly. They would look back toward Earth for the final time as their spacecraft departed, watching their home world slowly shrink into a distant point of light before turning forward toward Mars, toward their future, toward the place that would become home. This is the real reason the first humans on Mars may never return to Earth. Not because the mission failed, not because disaster trapped them there, not because humanity abandoned them, but because returning home was never part of the objective. The goal is to remain, to build, to demonstrate that humans can survive and thrive on another world, to begin humanity's expansion across the solar system and eventually far beyond it. It would demand a tremendous sacrifice while also offering an extraordinary opportunity. Those first settlers would surrender everything they once knew on Earth: familiar comforts, lifelong routines, relationships with family and friends, the experience of breathing open air, hearing rainfall, and seeing green life spread across the landscape. In exchange, they would endure a difficult existence on a freezing desert world where survival depends on constant caution and where catastrophe could always be one malfunction away. But they would also gain something nobody in human history has ever possessed before. They would be the first humans to truly live on another planet, the first people to call a different world home, the first to prove that humanity's future does not end on Earth. Their names will live permanently in the pages of history. Children born hundreds of years from now, raised inside enormous Martian cities populated by millions of people, will study the first settlers the same way we study the passengers aboard the Mayflower or the explorers of the Lewis and Clark expedition. And those future generations on Mars, growing within a flourishing civilization filled with terraformed regions containing breathable air and flowing liquid water, may look back at the original colonists with both admiration and disbelief. They may struggle to truly understand how brutal those early years were, how much bravery was required, how enormous the sacrifices had been. In many ways, it's similar to how people today sometimes overlook the hardships faced by Earth's earliest settlers. The men and women who crossed dangerous oceans in wooden ships, who established communities in untamed wilderness, who endured freezing winters without modern medicine, electricity, or reliable heat. But that's the way progress has always worked. The goal was never for future generations to endure the same suffering as the pioneers who came before them. The purpose of pioneers is to make life less difficult for everyone who follows, to construct the first shelters that future settlers can enlarge into cities, to plant the first experimental crops that later generations can refine into reliable agriculture, to create the first infrastructure that future engineers can strengthen, redesign, and expand across an entire world. To make the early mistakes so later colonists won't have to repeat them. To carry the burden of being first. That has always been the responsibility of explorers. They enter places nobody has gone before. They confront dangers no one fully understands. They solve problems that once seemed impossible and open pathways for others to continue forward. The first settlers on Mars will do exactly the same thing. They'll leave Earth fully aware they are never returning, accepting that sacrifice as the cost of becoming part of history, of contributing to something greater than themselves. And when their spacecraft finally nears Mars after 6 to 9 months of travel through deep space, when they prepare for that terrifying descent through the thin Martian atmosphere, when the landing engines fire and the vehicle settles onto the surface, they'll open the hatch for the very first time. They'll step onto rust-red ground beneath a pale pink sky and leave humanity's first footprint on another planet. They'll say the first human words ever spoken from Martian soil. They'll stare upward at the distant, smaller sun, at unfamiliar constellations, at the 2 tiny moons rushing across the sky overhead, and in that moment they'll realize something extraordinary. They are home. Not on Earth anymore. Not ever returning there. But home all the same. Because home is not simply the place where you were born. Home is where you create your future, where your work matters, where you become part of a community striving toward a common purpose. And for the first Martian colonists, that home will be a harsh and unforgiving new world filled with danger, isolation, and endless challenges, yet also overflowing with possibility. They'll build that future slowly, one day after another. They'll enlarge the habitats, drill deep beneath the surface searching for frozen water, maintain the greenhouses, perform scientific research, explore the alien terrain, and gradually, over years and decades, reshape a dead planet into something that begins to feel alive. Not Earth, and never a replacement for Earth, but something entirely new, something human, something that demonstrates our ability to adapt, to survive in impossible conditions, to thrive in environments that should destroy us. And while all of this unfolds on Mars, Earth will continue turning millions of miles away. People will still be born. People will still die. Nations will rise, collapse, and rebuild. Civilizations will continue evolving. And eventually, if humanity survives its own dangers, if we overcome the threats capable of ending our existence, more missions will leave Earth for Mars. More settlers will commit to that one-way voyage. The Martian population will increase from dozens to hundreds, from hundreds to thousands, from thousands to millions. And someday, perhaps centuries into the future, Earth and Mars may stand together as sister worlds. Two planets supporting human civilization. Two homes for a species that began on one world, but refused to remain trapped there forever. Two branches of humanity sharing the same origins while slowly developing along different paths, each shaped by different environments, different hardships, and different victories. That future begins with the first settlers. The ones who leave Earth behind and never return. The ones who exchange one world for another. The ones who become, in the most literal way imaginable, aliens themselves. Humans living on an alien planet, adapting to alien conditions, and perhaps, after thousands of generations, evolving into something uniquely Martian. This is why the first humans on Mars may never come back. Not because the mission failed, not because they became prisoners, but because they achieved something greater than any earlier generation of explorers ever accomplished. They did not merely visit another world. They made it their world. They claimed a second planet for humanity. They proved that our species can leave its birthplace, survive elsewhere, and someday become not only multiplanetary, but eventually multistellar. The very first footprints left on Mars may remain there forever. The planet has no powerful rainstorms to erase them, no rivers to wash them away, no forests or grasses to grow over them. Those marks in the Martian dust could survive for millions of years. A lasting monument to the instant humanity first crossed the boundary from being a civilization tied to one planet into becoming something far greater. And the individuals who leave those first footprints behind, who inhale processed Martian air, drink endlessly recycled water, and survive on hydroponic crops cultivated beneath artificial LED lighting, who stand beneath alien skies, watching Earth disappear below the horizon while knowing they will never walk on that distant world again. Those individuals represent heroism in its purest form. They are surrendering everything they once knew, every comfort, every routine, every easy certainty, so a future can exist that many of them will never personally witness. That is the real reason they will not return. Because returning would mean walking away from the very future they sacrificed everything to create. And these are not people who walk away from unfinished work. These are the kinds of people who recognize when something must be done, something humanity has never accomplished before, something whose consequences will continue echoing across history for as long as human beings survive. And instead of hesitating, they answer with a simple decision. Yes, I'll do it. I'll go. I'll remain there. I'll help build a new beginning on another planet. And when those original settlers eventually grow old, after decades spent living beneath Martian skies, after younger generations arrive, some of whom were only children when the first mission launched, and others who had not even been born yet, those first pioneers will be able to reflect on their lives, knowing they participated in something truly extraordinary. They will not regret their choice. They will not spend their final years wishing they had remained on Earth. They will understand that they made the correct decision because they will be able to see the results with their own eyes. Not only shelters, agricultural systems, and machinery, but an actual civilization, a society, a human home established on another world. They will watch children running through pressurized playgrounds, learning to move through the unusual low gravity where every stride naturally becomes a light bounce. They will witness scientists uncovering answers to mysteries humanity has wondered about for centuries. Where did the water on Mars disappear to? Did life once emerge there? How does a planet transform from a young, violent world into an ancient frozen one? What happens to the human body after generations exposed to reduced gravity and constant radiation? Those mysteries will finally be answered because colonists stayed long enough to investigate them. They will watch engineers overcome problems once considered nearly impossible. How do you produce electronics without the enormous supply chains available on Earth? How do you construct habitats using local resources when those resources are completely unlike terrestrial materials? How do you preserve advanced technology in an environment that continuously attempts to damage and destroy it? The first generation will wrestle with those difficulties every single day. The second generation will improve the methods. By the third generation, the solutions will be so refined and reliable that they will simply become ordinary Martian procedure, the normal way life operates there. They will witness artists creating works inspired by the uniquely Martian experience in ways no Earthbound person could ever completely understand. Paintings capturing the exact pink tone of the Martian sunset, where the blue slowly drifts toward purple and airborne dust bends light into patterns unlike anything seen on Earth. Sculptures carved from Martian stone by artists who understand how rock fractures differently under weaker gravity. Music written for modified instruments designed to function within a thin, low-pressure atmosphere, where sound behaves differently from the way it does on Earth. Poetry created during silent Martian nights, while Phobos and Deimos race overhead and Earth appears only as a bright point of light, barely distinguishable from Venus. They will witness communities taking shape, traditions emerging, and holidays becoming part of everyday life. Weddings celebrated inside greenhouses surrounded by the crops responsible for keeping everyone alive. Memorial ceremonies held for those who died there, their ashes scattered across the Martian surface, so they literally become part of the planet they help transform. Every funeral serving as a reminder that this mission was always permanent, that these people truly gave their lives for this vision. They arrived on Mars, and they remained there until the very end. And they will understand that their decision to leave Earth forever is what allowed all of it to happen. Without their courage, their sacrifice, and their willingness to abandon everything familiar, none of this would exist. Mars would have remained an empty and silent world, still waiting for someone courageous enough to claim it as home. But they were courageous enough. They went there. They stayed there. And they created a future. The emotional weight of understanding that truth would be immense. They would realize that their names will be taught to every child born on Mars for as long as human civilization survives on that planet. In the same way children on Earth learn about the Wright brothers, Neil Armstrong, or Marie Curie, individuals who permanently expanded the limits of what humanity believed possible. Before the Wright brothers, human beings could not fly. After them, they could. Before Armstrong, humanity was confined entirely to Earth. After him, humans had walked across another world. Before the first Mars settlers, humanity existed as a civilization tied to a single planet. After them, humanity became a multi-planet species. The transformation of humanity from a species confined to a single planet into one capable of living across multiple worlds may become one of the greatest turning points in the entire story of life on Earth. For 3.8 billion years, every living thing existed only here, on this planet. Every organism that ever emerged, from microscopic bacteria to enormous animals and complex plant life, lived its entire existence within a thin layer surrounding Earth's surface. Every one of us comes from the same original spark of life. We are all connected through one immense family tree, all built from the same DNA framework, all relying on the same core chemistry, the same dependence on liquid water and carbon-based biology. Then humanity created technology. We learned how to study the universe through observation, experimentation, and mathematics. We designed machines capable of escaping Earth's gravity. We launched robotic probes toward distant planets, collecting information, testing ideas, and steadily increasing our understanding of reality. And eventually, we reached the point where we could send human beings beyond Earth permanently, establishing a lasting presence away from the planet where our species began. That ability changes the future completely. It means that if disaster strikes Earth, even on the worst imaginable scale, extinction no longer has to mean the end of humanity. A massive asteroid collision, a supervolcano eruption, a global pandemic, nuclear conflict, uncontrolled climate collapse, any one of these events could destroy Earth's ecosystems and wipe out most or even all humans living here. But if human communities exist on Mars, if self-sufficient settlements survive across more than one world, then humanity continues. Everything our species has learned, every scientific discovery, every piece of art, every story and memory and achievement, all of it survives with those distant colonies. Civilization could eventually recover, rebuild itself, and perhaps even return to Earth if the planet becomes habitable again. Or humanity could continue spreading farther outward if Earth remains hostile forever. This is not simply theoretical disaster planning. Earth has already experienced extinction-level catastrophes in the past, and eventually it will again. 66 million years ago, an asteroid roughly 10 kilometers wide slammed into the region now known as the Yucatan Peninsula. The collision unleashed energy equal to billions of nuclear bombs. Dust and debris were blasted into the atmosphere in such enormous quantities that sunlight was blocked for months, possibly years. Plants could no longer perform photosynthesis. Entire food chains collapsed. The dinosaurs, which had ruled land ecosystems for 160 million years, disappeared, along with nearly 75% of all species living on Earth. And that was not the only mass extinction event our planet has endured. Around 252 million years ago, the Permian-Triassic extinction devastated life on Earth, eliminating approximately 96% of marine species and 70% of land vertebrates. Scientists still debate the exact cause. It may have involved volcanic eruptions on scales beyond anything humans have ever witnessed, or perhaps an asteroid impact, or several catastrophic events happening together. Whatever triggered it, Earth's biosphere came frighteningly close to complete collapse. Life survived only barely, and evolution required tens of millions of years to refill the planet with new forms of life. But intelligence, self-awareness, and civilization are extremely recent developments. Anatomically, modern humans have existed for roughly 300,000 years. Civilization with agriculture, cities, and written language has existed for only about 10,000 years. We are incredibly new arrivals on a world that is 4.54 billion years old. We still do not know whether consciousness is common throughout the cosmos. We do not know whether intelligence naturally appears whenever conditions become suitable and enough time passes. We do not know if technological civilization is a normal consequence of evolution or an unbelievably rare accident that has happened only once within the observable universe. But we do know that consciousness exists here, right now, on this planet. We know intelligence exists, we know civilization exists, and we also know how vulnerable these things are to disasters completely indifferent to their value. Becoming a species that lives on multiple planets is protection against that vulnerability. It is similar to creating backups of irreplaceable data in several different locations. If one location is destroyed, another remains, allowing recovery. This is not about abandoning Earth or losing hope in our home world. It is about wisdom. It is about understanding that sometimes the safest way to preserve something precious is to avoid placing all of it in a single fragile location. The first settlers on Mars would feel this reality deeply and personally. They are the backup. They are the safeguard. Their very existence on another world means humanity can endure catastrophes that might otherwise erase us forever. They would accept uncomfortable living conditions, surrender ordinary human comforts, and expose themselves to enormous health risks because they understand what is at stake. They would not be making those sacrifices only for themselves. They would be doing it for the survival of the species, for future generations, for the chance that human awareness and civilization continue even if Earth someday becomes unlivable. There is also a philosophical meaning behind all of this that extends far beyond simple survival. Human beings have always explored. Our species began in East Africa and eventually spread across the entire Earth, reaching every continent and adapting to every environment imaginable, from frozen Arctic landscapes to tropical rainforests to thin-air mountain plateaus high above sea level. Humanity crossed vast oceans in fragile wooden boats, guided only by the stars overhead, the movement of currents, and the behavior of birds flying across the sky. We climbed the tallest mountains on Earth, not because there was practical value waiting at the peak, but because those summits existed, and people wanted to know what it felt like to stand there. The desire to explore, to move beyond limits, to discover what lies past the horizon is woven deeply into human nature itself. Some individuals are perfectly happy remaining where they are, living within familiar routines, surrounded by predictable environments and established traditions. Others experience something different, a constant pull toward movement, discovery, and new experiences. Both are completely human responses. Society depends on both kinds of people. We need those who preserve stability, who improve existing systems, who create homes, communities, and safe environments where families can thrive. But we also need those willing to step into uncertainty, to accept danger, to venture into places nobody has gone before, and return with knowledge about what exists there and whether others might survive following the same path. The first settlers on Mars would belong to that second category. They would be the pathfinders, the pioneers, the first wave of people willing to go ahead so future generations could arrive with greater safety and understanding. They would accept enormous risks because they understand that someone must go first, and they willingly choose to become those people. This mindset is not recklessness, nor is it some desire for self-destruction. It is bravery grounded in a realistic understanding of danger. They would fully understand the hazards involved, yet they would still move forward because the importance of the mission matters more to them than fear itself. Human history celebrates people like this. We build statues to explorers and pioneers. We pass their stories to children and present them as examples of humanity at its most courageous and capable. The first permanent settlers on Mars would deserve the same kind of recognition, not simply because they traveled to another planet, but because they remained there, committed themselves to it, and created something lasting. They would transform humanity's theoretical ability to live on another world into an undeniable reality. Before them, living on another planet would exist only as an idea. After them, it would become part of human existence. Their willingness to never come back to Earth would become one of the defining parts of their legacy. They could have demanded systems for returning home. They could have insisted on ascent vehicles, fuel production facilities, and all the infrastructure required for a safe return trip. But they would also recognize that demanding a return capability would make the mission dramatically more difficult and vastly more expensive, perhaps even impossible, within the limits of current technology and available budgets. So instead, they would accept a journey without return. They would give up Earth permanently. They would make an extraordinary sacrifice, not by dying immediately, but by surrendering forever the possibility of returning to the world where they were born and raised. That sacrifice could be the very thing that allows the mission to exist at all. It would reduce costs, simplify mission design, and allow resources to focus entirely on creating a sustainable settlement rather than preparing people to leave Mars again. Every kilogram not devoted to ascent fuel becomes a kilogram available for greenhouses, machinery, medical equipment, scientific tools, spare parts, or supplies that make survival on Mars easier and help the colony expand. And expansion would be absolutely necessary. A settlement containing only 4 to 6 individuals is not a civilization. It is merely a foothold. Such a tiny community would remain dangerously vulnerable to accidents, technical failures, or random bad luck. Losing even 2 people could threaten the survival of everyone else, because there might not be enough remaining colonists to operate and maintain all essential systems. But a settlement of 40 people creates redundancy. A settlement of 400 allows specialization, where some individuals become doctors, others engineers, farmers, teachers, technicians, or scientists. A settlement of 4,000 begins developing culture, economy, governance, and social structure. At that point, it starts becoming truly self-sustaining, not only technologically, but psychologically and socially as well. Reaching the point where a colony grows from 6 people to 6,000 would require continuous support missions from Earth, especially during the early decades. Every mission would deliver additional settlers, new machinery, broader genetic diversity, and more specialized knowledge. The growth could become exponential if each successful mission increases public excitement, attracts more funding, and inspires more volunteers. Or growth might remain slow and linear, with missions arriving only every few years, whenever governments and organizations can afford them. It could also stagnate entirely if missions fail, if public enthusiasm fades, or if political priorities on Earth change over time. History provides examples of every possibility. European settlement in the Americas began slowly, suffered repeated failures, and later expanded rapidly. Once success became visible and economic opportunities attracted enormous investment. Antarctic research stations, on the other hand, remained small and expanded only gradually because there has never been a strong economic reason to support massive populations there. Modern space station programs have already demonstrated that humans can maintain a continuous presence inside extremely hostile environments, but they have also revealed how politically fragile such efforts can be, dependent on funding, cooperation, and international priorities that may disappear when governments change. Colonization of Mars would probably experience repeated cycles of growth and decline. The early years could bring enormous excitement and rapid expansion as successful missions capture humanity's imagination. Then progress might slow as the true difficulty of surviving on Mars becomes impossible to ignore and costs continue rising higher. And there is always the possibility of collapse if a catastrophic accident kills settlers or if economic crises on Earth force governments to slash space exploration budgets entirely. After that, there would likely be slow recovery periods as advancing technology lowers expenses or entirely new reasons for expansion appear. The general direction would still move forward, but not without setbacks, crises, and long stretches of hardship that challenge the determination of everyone participating. The first settlers would witness the early excitement of the colony, but many of them might never live long enough to see the complete vision they helped begin. By the time they finally landed on Mars, they would probably already be in their 40s or 50s, after enduring years of preparation, testing, and selection. They might spend another 20 to 30 years living on Mars, dedicating themselves to constructing the settlement, greeting incoming crews, and teaching newcomers the difficult lessons they learned through experience. Eventually, age would catch up with them. Their bodies would likely deteriorate more rapidly than they would have on Earth because of radiation exposure and the long-term consequences of low gravity. Most would probably spend their final years on Mars, reaching old age somewhere in their 70s or 80s, surrounded by a settlement that started small but steadily grew into a real community. Their funerals would become deeply meaningful events for everyone living there. Every resident on Mars would likely attend. People would gather inside the largest pressurized structure available, telling stories about the person who passed away, honoring everything they contributed, mourning together as a community. Afterward, the body would be carried outside in a solemn procession, spacesuits moving carefully through the weak Martian gravity before being entrusted to the Martian surface itself. Traditional burial methods would not be practical because the frozen ground and permafrost would make excavation extremely difficult. More likely, the body would rest in a designated memorial area, protected beneath stones and marked with a modest monument. That place would become the first cemetery on Mars, where the earliest builders of human civilization on another planet remain forever. Colonists arriving years later, or even decades afterward, would probably visit that cemetery almost like a sacred pilgrimage. They would stand quietly before the markers of the original settlers and think about the courage required to come to a world they knew they might never leave again. Children born on Mars would study these people in school. They would learn about the choices these pioneers made and understand that their own lives became possible only because others accepted a one-way journey. And among those later generations of arrivals, there could eventually be grandchildren of the original colonists. Some might have been very young when a parent left Earth for Mars. Others may not even have been born yet. They would grow up hearing stories about a mother, father, aunt, or uncle who departed for Mars long ago. They would watch recordings of the landing, listen to messages transmitted across millions of kilometers, see images of the red deserts and distant horizons, and slowly decide that they wanted to witness that world themselves. They would want to follow the same path as their relatives and become part of the same enormous human project. These second-generation migrants to Mars would arrive and discover a world their family member helped build with their own hands. They would walk through habitats their relative helped construct. They would eat crops grown inside greenhouses their relative helped design. They would meet men and women who worked beside that family member for decades, people capable of sharing stories, memories, and moments from a life lived far away from Earth. And if fortune allowed it, if the timing aligned perfectly, they might arrive while that relative was still alive, still aware enough to recognize them, still capable of understanding that someone from Earth crossed the gulf between planets just for one final reunion. Imagine that moment. An elderly colonist, physically changed by decades of radiation and low gravity, body weakened and curved with age, mind perhaps slower but still present, suddenly seeing someone connected to the life they left behind 30 years earlier. A daughter, now middle-aged herself, who accepted the dangerous 6 to 9 month voyage to Mars, knowing there was a chance her parent would die before she arrived. They would hold each other as best they could through bulky spacesuits, or perhaps properly if they were safely inside a habitat without the restrictions of life support equipment. They would spend hours talking, then days. They would exchange stories about entire lifetimes separated by 2 worlds and decades of distance. The colonist would speak about everything Mars taught them, about the struggle of creating a society from almost nothing, about the fulfillment that comes from watching an impossible dream slowly become real. The daughter would bring stories from Earth, updates about relatives and old friends, news about technologies, customs, and cultural changes that the colonist only experienced indirectly through transmissions and reports. Then eventually, the old colonist's life would come to an end. But in those final moments, they would know their family came for them. They would know the connection to Earth was never entirely broken. They would understand that love can survive even the enormous distance between planets, even when the journey itself requires 30 years to complete. Their last days would unfold on Mars, the world they deliberately chose, surrounded by the community they helped establish, with family beside them at the end. Considering everything, there are worse ways a person could leave this world. In many ways, it would be kinder than what countless people experience on Earth. Stories like these would eventually become woven into the culture of Mars itself. The family divided across 2 planets. The pioneer who never saw Earth again, yet whose children later came to Mars. The sacrifice. The reunion. The permanent distance, mixed with an unexpected reconnection. These stories would help future Martians understand who they are, how they are connected to Earth, and what choices allowed their civilization to exist in the first place. Because every single person living on Mars would only be there because someone, somewhere, made a decision. Some of them would have made the decision to travel there themselves, while others would have arrived because their parents chose that path, either bringing them as children or having them after settling on Mars. Nobody living on Mars would exist there by chance. No Martian would simply end up there through default circumstance without some deliberate decision somewhere in their family history. That alone would shape a society profoundly different from Earth, where most people remain in the place where they were born, following lives shaped more by circumstance than by conscious choice. People raised on Mars would grow up fully aware that their existence depended on someone making an intentional decision. Humanity would not be on Mars because of accident or natural evolutionary destiny, but because certain individuals deliberately chose to leave Earth, remain there permanently, and build something new. That understanding could create a civilization that deeply values intention, one that views life as something people actively shape, rather than something that merely unfolds around them. Or perhaps it would create an entirely different burden. A pressure to justify your existence, a feeling that you must prove worthy of the immense sacrifices made by those who came before you. More likely, Martian society would contain elements of both ideas at once, a culture empowered by its history, while also carrying the heavy responsibility of living up to it. Human cultures on Earth evolved slowly over thousands of years, influenced by climate, geography, migration, warfare, trade, available resources, technological progress, and countless unpredictable historical events. Martian culture would emerge under very different conditions. Its development would be compressed into mere decades or centuries, shaped above all by survival on a hostile world and by the collective identity of being pioneers. The earliest settlers would define the foundations. They would establish the first customs, create the original traditions, and build the myths future generations would inherit. Later arrivals would reshape those ideas and add new layers to them. Children born on Mars would absorb that culture, reinterpret it, and transform it again. Within only a few generations, Martian society could become dramatically different from the cultures of Earth. Language itself would evolve. New vocabulary unique to Martian life would appear, and entirely new grammatical habits might eventually emerge. Social expectations would adjust to existence inside enclosed habitats, where resources remain limited and every person depends on everyone else. Cultural values would increasingly emphasize cooperation, sustainability, and long-term thinking, because individual survival would be inseparable from the survival of the community itself. Art, philosophy, and intellectual life would also reflect the realities of Mars. Creative works shaped by the Martian experience might eventually feel strange or even impossible for people on Earth to fully understand, despite both populations sharing the same human origins. And the first settlers, the people who accepted the one-way journey, would eventually become legends. Their genuine hardships, mistakes, fears, and imperfections would slowly fade from memory, replaced by idealized stories designed to serve the emotional and cultural needs of later generations. They would become heroic symbols, larger-than-life figures, representing the qualities Martian civilization most admired and wished to encourage. The reality of who they truly were, ordinary people with extraordinary bravery, who made an irreversible decision and endured its consequences, might disappear beneath the mythology. But that is how human cultures have always functioned. Civilizations create stories about their beginnings that help explain who they are in the present. Those stories do not need to be perfectly factual to carry meaning. What matters is that they communicate deeper truths, helping people understand their origins and the reasons their society exists at all. By choosing never to return to Earth, the first Mars settlers would give future Martians an incredibly powerful origin story. They would be remembered as the pioneers who permanently left their home world behind to create another one, people willing to sacrifice everything familiar because they believed something new and better could exist elsewhere. They gambled their lives on the belief that humanity could survive and flourish on Mars, and in the end, they proved that belief correct. That story would inspire generation after generation. Children would grow up hearing it while learning the history of their world. Leaders would reference it during moments when society needed unity and shared purpose. Individuals facing difficult decisions would remember it quietly when they needed strength or courage. The story of the first colonists who never returned, not because they failed, but because returning was never meant to happen. The mission was always to remain, to construct a civilization, to transform Mars from a barren planet into a true home. And by carrying out that mission, by living through that reality, they would achieve something no humans before them had ever accomplished. They would demonstrate that humanity can survive beyond the planet where it first evolved. They would prove that our species can adapt to environments radically different from the conditions that shaped us. Human awareness, culture, and civilization would no longer belong exclusively to Earth. They could expand outward, establish roots elsewhere, and endure permanently across multiple worlds. That is more than exploration, more than adventure. It is a form of existential protection for humanity itself. It is the moment when evolution stops being entirely passive and becomes something our species consciously directs toward long-term survival across cosmic timescales. It is humanity ensuring that no matter what eventually happens to Earth, whether sudden disaster, slow collapse, or simply the distant transformation of the sun into a red giant billions of years from now, human civilization continues somewhere else. Our ideas, our creativity, our understanding, our awareness, everything that defines us as human beings, continues to survive and expand and transform until it eventually becomes something beyond anything we can currently foresee or fully comprehend. Thank you for being part of this journey into understanding why the first settlers on Mars may choose a mission with no return to Earth. If these ideas made you think more deeply about humanity's future, leaving a like or subscribing would help this channel continue exploring these profound questions about our place in space. Creating thoughtful explorations about what space travel truly means requires enormous time, reflection, and research to do correctly. The path toward Mars is about far more than engineering or scientific success. It signals a complete change in the way humanity understands itself as a species. For the first time in history, we are no longer limited to a single planet. We now possess both the knowledge and the technological ability to expand throughout the solar system. Whether humanity ultimately decides to move forward, whether we are willing to dedicate the resources and accept the sacrifices required, is still uncertain. But if we do, if those first spacecraft depart and those first settlers arrive and remain and begin building something permanent, they will accomplish something no earlier generation was capable of achieving. They will turn humanity into a species that exists on multiple worlds. They will help secure the long-term survival of human civilization. They will open the doorway to a frontier that could allow humanity to continue exploring, learning, adapting, and evolving for thousands or perhaps millions of years. And everything begins with individuals willing to accept a one-way mission, people prepared to leave Earth behind forever for the opportunity to help create that future. That is more than exploration. It is transformation. It is evolution. It is humanity advancing to the next stage of its existence. And those first footsteps pressed into the Martian surface, the ones that may remain untouched for ages, will represent the instant humanity took that next step, the moment we proved it was possible, the moment we decided to reach towards something greater than ourselves. That is why they may never return, because they will be creating something destined to endure far beyond a single lifetime, something capable of surviving longer than countries and empires, something that may continue existing as long as human beings live anywhere in the universe. They will not come back, because, in a profound sense, they will already have arrived home, to a different home, to Mars, and that is where they will remain.